On the morning of March 15, 1944, Hauptmann Werner Schroer stood beside his Messerschmitt Bf 109 Gustav VI, watching mechanics drain oil that had turned to sludge after just 43 hours of operation. The 28-year-old ace, credited with 114 kills on the Eastern and North African fronts, ran his hand along the engine, cowling with the weary familiarity of a man who understood that Germany's most sophisticated fighter aircraft was being slowly strangled by its own power plant. The Daimler-Benz DB605A engine beneath that cowling represented the pinnacle of German engineering, a supercharged 12-cylinder inverted V design that produced 1,475 horsepower at takeoff. It was precise, powerful, and temperamental. After 40 hours of combat operations, it required complete overhaul. After 60, if you were lucky, it needed replacement. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Across the English Channel, Flight Lieutenant James Harrington of No. 611 Squadron RAF settled into the cockpit of his North American P-51 Mustang, an aircraft powered by an engine that would run for 100 hours between major overhauls at full combat power, sometimes longer. The Packard V-1650 Merlin, manufactured in a Detroit factory by workers who'd been building luxury automobiles just 3 years earlier, was about to invalidate every assumption German engineers held about the limits of aircraft engine endurance. This wasn't just about engineering specifications on paper. This was about mathematics so brutal they would reshape the entire air war over Europe. If your engine needed overhaul every 40 hours and your enemies ran for 100, he could fly 2.5 times as many combat missions with the same number of engines. He could maintain larger standing forces. He could press attacks when you were grounded for maintenance. He could own the sky through sheer operational availability. The story begins not in 1944, but in May of 1940, when Britain stood alone against Nazi Germany and faced the very real possibility of invasion. The Royal Air Force's Fighter Command had fought the Battle of France with Hawker Hurricanes and Supermarine Spitfires, both powered by Rolls-Royce Merlin engines. The Merlin was superb, a liquid-cooled V-12 design that represented decades of British engineering refinement. But Rolls-Royce's production capacity, concentrated in Derby and Crewe, couldn't possibly meet the demands of total war. Britain needed Merlins by the thousands, and Rolls-Royce could produce them only by the hundreds. The British Purchasing Commission, led by the industrialist Henry Self, made a desperate proposal to American manufacturers. Could anyone in the United States produce Merlin engines under license? The technical challenges were staggering. The Merlin incorporated over 10,000 individual parts, machined to tolerances measured in thousandths of an inch. British manufacturing used imperial measurements, while American industry worked in different standards. The engine's components required specialized metallurgy, heat treatments, and assembly techniques that existed nowhere in the American automotive industry. Ford Motor Company examined the specifications and declined. The Merlin was too complex, too demanding, and Henry Ford himself, still harboring isolationist sympathies in 1940, saw no profit in British desperation. General Motors expressed interest but couldn't commit capacity while maintaining its existing military contracts. Then the British approached Packard Motor Car Company of Detroit, a luxury automobile manufacturer known for precision engineering and quality control. Packard's president, George Christopher, reviewed the British proposal with his chief engineer, Colonel Jesse Vincent, a legendary figure in American automotive engineering who designed the Liberty engine that powered American aircraft in the First World War. Vincent spent 3 weeks analyzing Rolls-Royce blueprints and technical specifications that filled 17 crates. His assessment, preserved in Packard Company archives, concluded that producing the Merlin in America would require completely rethinking how the engine was manufactured. British production relied on skilled craftsmen who hand-fitted components, filed parts to achieve proper tolerances, and used techniques that worked beautifully in limited production but couldn't scale to mass manufacturing. Packard would need to redesign hundreds of components to accommodate American machine tools, substitute American materials for British alloys that weren't available in the United States, and create entirely new manufacturing processes that achieved the same performance through precision mass production rather than artisan craftsmanship. Christopher and Vincent told the British they could do it, but it would take time and cost money. Lots of money. The British, facing invasion and desperate for engines, agreed to everything. The contract, signed in September 1940, called for Packard to produce 6,000 Merlin engines at roughly $9,000 per unit. Packard would absorb all tooling costs, estimated at over $4 million, a staggering investment for a company whose annual profits had never exceeded $6 million. This wasn't business calculation. This was a bet on survival, both Britain's and ultimately America's. The technical challenges began immediately. Rolls-Royce sent complete Merlin engines and detailed blueprints to Detroit, but British engineering drawings used terminology, symbols, and conventions unfamiliar to American engineers. A British technical liaison team, led by Rolls-Royce engineer Ronald Harker, spent months at Packard's Detroit factory, translating not just measurements but entire conceptual approaches to manufacturing. Where Rolls-Royce specifications called for components to be hand-fitted to smoothness, Packard engineers needed to define exact numerical tolerances that machines could achieve consistently. Where British drawings specified best quality steel, Packard metallurgists had to identify specific American steel grades with equivalent properties. Vincent assembled a team of over 100 engineers who spent 6 months redesigning the Merlin for American production. They modified the crankshaft to use different bearings available in the United States. They redesigned the supercharger housing to accommodate different casting techniques. They changed dozens of fasteners from British Whitworth threads to American standard threads. They substituted American magnetos, carburetors, and instruments for British components that couldn't be sourced domestically. The result was designated the Packard V-1650, identical in performance to the Rolls-Royce Merlin, but manufactured with 400 documented changes to accommodate American production methods. Building the engines required creating an entirely new factory. Packard constructed a facility on Morse Avenue in Detroit, covering over 1 million square feet, equipped with machine tools ordered from across American industry. The company recruited workers from Detroit's automotive sector, men and women who understood precision manufacturing but had never built aircraft engines. Training programs ran around the clock, teaching machinists tolerances measured in 0.010 of an inch, teaching inspectors to identify microscopic flaws that could cause catastrophic failure at 25,000 feet. The first production Packard V-1650 rolled off the assembly line in August 1941. It was shipped to Britain, installed in a test stand, and run through evaluation protocols that pushed it to maximum power for hours at a time. British test engineers, skeptical that American mass production could match Rolls-Royce quality, watched instruments carefully for any sign of weakness. The engine performed flawlessly. Packard had achieved what Ford thought impossible, mass-producing a complex high-performance aircraft engine that matched the original in every measurable specification. But matching Rolls-Royce performance was just the beginning. What happened next would change everything the Germans thought they knew about engine reliability. Packard's mass production techniques, the very methods British craftsmen initially viewed with suspicion, created engines with unprecedented consistency. Where hand-fitted Rolls-Royce Merlins varied slightly from unit to unit based on the individual craftsman's work, Packard V-1650s came off the production line with tolerances so uniform that components were genuinely interchangeable. A piston from one engine fit perfectly in another. Bearings, rods, valves, every component matched specifications so precisely that field mechanics could swap parts between engines without adjustment or fitting. This consistency translated directly into reliability. Engines that ran to tighter, more consistent tolerances experienced less vibration, more even wear patterns, and fewer unexpected failures. The Germans, with their emphasis on artisanal precision and individual craftsman skill, had inadvertently created power plants that were less reliable than American mass-produced alternatives. It was a profound irony that would cost the Luftwaffe dearly. By December 1941, when Japanese bombs fell on Pearl Harbor and America entered the war.
If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this.
Packard was producing over 200 V-1650 engines monthly. Production would accelerate dramatically. In 1942, Packard delivered 4,000 engines. In 1943, that number reached 22,000. By the time production ended in 1945, Packard had manufactured over 55,000 V-1650 Merlin engines, accounting for roughly half of all Merlin production worldwide. These engines powered the aircraft that would dominate the skies over Europe. The North American P-51 Mustang, equipped with the Packard V-1650, became arguably the finest piston-engine fighter aircraft of the war. The Mustang's combination of range, speed, and combat performance allowed it to escort American bombers all the way to Berlin and back, a mission profile that would have been impossible with earlier short-range fighters. But the Mustang's success depended entirely on its power plant's extraordinary reliability. Oberleutnant Franz Stigler, a Luftwaffe fighter pilot who would later become famous for sparing a crippled American bomber, kept a detailed logbook throughout the war, portions of which survive in German military archives. His entries from early 1944 document a growing crisis in Luftwaffe fighter operations. Engine failures were becoming routine. Pilots were aborting missions due to mechanical problems at rates that would have been considered unacceptable a year earlier. Stigler's own Messerschmitt required engine replacement 4 times between January and July of 1944, each replacement taking his aircraft out of service for days or weeks, while mechanics installed new power plants and conducted test flights. The mathematics were crushing German fighter operations. A Jagdgeschwader, a fighter wing, typically maintained around 70 aircraft on paper. But with engines requiring overhaul every 40 to 60 hours and constant mechanical failures, actual operational availability rarely exceeded 50%. On any given day, half the unit's aircraft were grounded for maintenance, engine changes, or repairs. The Luftwaffe was losing the war of attrition not primarily through combat losses, though those were severe, but through simple mechanical unavailability. American fighter groups operating P-51 Mustangs experienced a completely different operational reality. The Packard V-1650's 100-hour time between overhauls meant pilots could fly more missions before their aircraft required major maintenance. Field maintenance crews spent less time on engine changes and more time on routine servicing. Operational availability rates for Mustang squadrons routinely exceeded 75%, sometimes reaching 85%. More aircraft available meant more missions flown, more bomber escorts provided, more ground targets strafed, more pressure applied to a German military machine that was being slowly crushed by superior Allied industrial capacity. The technical specifications told part of the story. The Packard V-1650 produced 1,690 horsepower at maximum combat power, slightly more than the Daimler-Benz DB605. But specifications mattered less than sustained operational performance. An engine that could run for 100 hours between overhauls while maintaining full power output represented a fundamental advantage that German engineers couldn't overcome through clever design or superior craftsmanship. Major Werner Molt, serving with Jagdgeschwader 3 on the Western Front, wrote in a letter to his wife in April 1944, "The Americans have engines that simply never fail. We face them knowing that if we survive the combat, our own machines may betray us on the flight home. It is a feeling I cannot adequately describe." The letter, preserved in German family archives and later donated to military historians, captures the psychological impact of facing an enemy whose technical reliability exceeded your own. German engineers understood the problem but couldn't solve it within the constraints of wartime production. The Daimler-Benz and Junkers engine plants were designed for moderate production of high-quality power plants using skilled labor. Attempts to increase production rates by simplifying manufacturing processes resulted in quality declines that made reliability problems worse rather than better. The German aviation industry found itself trapped between impossibilities. They couldn't produce engines fast enough to meet demand, and attempts to increase production reduced reliability, which increased demand for replacement engines even further. Packard's solution, mass production with precision tolerances, required industrial infrastructure and manufacturing expertise that Germany couldn't replicate under wartime conditions. American factories benefited from abundant raw materials, stable electrical power, and a workforce that wasn't being bombed nightly by enemy aircraft. German industry, by 1944, faced chronic shortages of strategic materials, Allied bombing that disrupted production, and desperate measures to maintain output that inevitably compromised quality control. The operational impact appeared most dramatically during major air battles over Germany in 1944. On March 6, 1944, the first American daylight raid on Berlin involved over 600 heavy bombers escorted by 800 fighters, most of them P-51 Mustangs with Packard V-1650 engines. The Luftwaffe's fighter response involved approximately 150 aircraft, limited not primarily by pilot availability, but by how many fighters had operational engines that day. The battle lasted several hours as American formations penetrated deep into German airspace, dropped their bombs, and fought their way back to England. Mustang pilots engaged German interceptors repeatedly, and the Packard Merlins performed flawlessly throughout missions that lasted over 6 hours from takeoff to landing. German pilots, conversely, experienced numerous engine failures and mechanical problems that forced them to break off combat or emergency land at the nearest airfield. Colonel Hubert Zemke, commanding the 56th Fighter Group, noted in his after-action report that his pilots encountered German fighters that seemed unwilling to press attacks, breaking off engagements even when they held tactical advantages. Intelligence officers initially attributed this to pilot quality declining as experienced German aviators were killed or captured. But debriefings of captured Luftwaffe pilots revealed a different story. They were nursing sick engines, managing mechanical problems, and desperately trying to preserve their aircraft for the flight home. The aggressive pursuit tactics that characterized earlier Luftwaffe operations were being abandoned not from fear, but from mechanical necessity. The technical specifications of the Packard V-1650 reveal why it achieved such extraordinary reliability. The engine displaced 1,649 cubic inches, roughly 27 liters, across 12 cylinders arranged in a 60-degree V configuration. Each cylinder measured 5 4/10 inches bore by 6 inches stroke, dimensions that represented decades of Rolls-Royce refinement for optimal power delivery and mechanical stress distribution. The two-stage two-speed supercharger, driven by the crankshaft through a sophisticated gear train, compressed incoming air to maintain sea-level power output at altitudes exceeding 25,000 feet. But specifications alone don't explain reliability. The secret lay in manufacturing precision and material selection. Packard's metallurgists developed proprietary steel alloys for critical components like crankshafts and connecting rods. These alloys combined strength with flexibility, allowing parts to withstand extreme stress without fracturing. The crankshaft, machined from a single steel forging, was balanced to tolerances measured in fractions of an ounce. Imbalanced rotating assemblies cause vibration, and vibration causes premature wear and failure. Packard's production crankshafts were balanced so precisely that engines could run smoothly at maximum RPM for hours without developing harmful vibrations. The cylinder heads, cast from aluminum alloy, incorporated cooling passages designed to maintain optimal temperatures throughout the combustion chamber. Overheating caused pre-ignition and detonation, both of which could destroy an engine in seconds. The Packard design used liquid coolant circulating through precisely engineered passages to remove heat efficiently while maintaining temperatures within the narrow range where the engine developed maximum power without mechanical stress. Piston design represented another crucial innovation. Each piston, machined from aluminum forgings, incorporated 3 compression rings and 2 oil control rings. The rings sealed the combustion chamber while allowing the piston to move freely within the cylinder. Packard engineers spent months optimizing ring tension, seeking the perfect balance between sealing efficiency and mechanical friction. Too much tension caused excessive wear. Too little allowed combustion gases to bypass the piston, reducing power and contaminating the oil. The production specification achieved the optimal compromise, and every piston received individual inspection to ensure it met exacting standards. The valve train, operating at speeds exceeding 3,000 revolutions per minute, required components that could withstand millions of cycles without failure. Intake and exhaust valves, made from heat-resistant steel alloys, operated in an environment of extreme temperature and pressure. The valve seats, into which the valves sealed during each cycle, were hardened to prevent erosion from hot combustion gases. Valve springs, carefully selected for precise tension and fatigue resistance, closed the valves reliably throughout the engine's operational life. Lubrication system design contributed significantly to reliability. The Packard V-1650 used a pressure lubrication system that delivered oil to every bearing surface under controlled pressure. The oil pump, driven by the crankshaft, maintained approximately 60 pounds per square inch of pressure throughout the engine. This ensured that a protective film of oil separated moving metal surfaces, preventing direct contact that would cause wear. The oil itself, specially formulated for aircraft engines, maintained its protective properties across temperature ranges from -40 degrees at high altitude to over 300 degrees near the combustion chambers. German engines incorporated similar technologies, but German manufacturing under wartime pressure couldn't maintain the consistency that Packard achieved. A Daimler-Benz DB605 produced in 1942, when German industry still had access to quality materials and skilled labor, was an excellent engine. The same engine produced in 1944, assembled with substitute materials and rushed through quality control, was significantly less reliable. Packard V-1650s, conversely, maintained consistent quality throughout the war because American industry never faced the resource constraints and production pressures that degraded German manufacturing. Lieutenant William Bill Overstreet of the 357th Fighter Group experienced the Packard Merlin's reliability during a mission that entered fighter pilot legend. On April 7, 1944, while escorting bombers over Germany, Overstreet engaged a Messerschmitt Bf-109 over Berlin. The German pilot, attempting to escape, dove toward the city at maximum speed. Overstreet followed, chasing the Messerschmitt through the streets of Berlin at rooftop level, a pursuit that took both aircraft through the span of the Brandenburg Gate itself. The Packard V-1650 and Overstreet's Mustang ran at maximum power throughout the pursuit, subjected to violent maneuvering and extreme throttle changes as he followed the German fighter through the urban landscape. The engine never hesitated, never faltered, delivering full power on demand, while Overstreet concentrated entirely on flying. When he finally shot down the Messerschmitt, his engine had been at combat power for over 15 minutes of the most demanding flying imaginable. He flew the same aircraft back to England without incident, the Packard Merlin running smoothly throughout the return flight. Technical reports from Wright Field, the U.S. Army Air Force's primary testing facility, documented the Packard V-1650's performance characteristics through exhaustive testing. Engineers ran engines on test stands for hundreds of hours, deliberately pushing them beyond operational limits to identify failure modes. The standard test protocol called for running engines at maximum combat power, 1,690 horsepower, at 3,000 RPM, for extended periods. Packard Merlins routinely exceeded 100 hours at these power settings before requiring major overhaul. The test reports, preserved in National Archives collections, reveal something remarkable. The engines didn't fail catastrophically when they finally required overhaul. Instead, they showed gradual degradation in performance, measurable decreases in compression, slight increases in oil consumption, predictable wear patterns that indicated overhaul was approaching. This predictability allowed maintenance crews to schedule overhauls proactively rather than responding to sudden failures. An aircraft commander knew that an engine with 90 hours of operation had perhaps 10 to 15 hours remaining before overhaul. He could plan missions accordingly, ensuring his aircraft remained operational when needed most. German engines, conversely, failed unpredictably. A Daimler-Benz with 30 hours of operation might run flawlessly, or it might suffer catastrophic bearing failure without warning. This unpredictability forced German maintenance crews into reactive postures, constantly responding to unexpected failures rather than managing scheduled maintenance. The operational impact was devastating. American squadrons could predict with reasonable accuracy how many aircraft would be available for any given mission. German units never knew until the morning briefing how many fighters would actually start their engines and take off. Major George Preddy, the highest-scoring American ace flying P-51 Mustangs in the European theater, credited the Packard Merlin with enabling the aggressive tactics that made him so successful. In interviews conducted after particularly successful missions, Preddy explained that knowing his engine would perform reliably allowed him to focus entirely on combat tactics. He didn't need to monitor engine instruments constantly, didn't need to worry about mechanical failure during critical moments. and could push his aircraft to its limits without fear that the engine would quit unexpectedly. This psychological advantage mattered as much as the technical specifications. German pilots, flying aircraft with unreliable engines, developed defensive habits. They monitored instruments constantly, worried about every unusual sound or vibration, and held back from fully committing to combat because engine failure during a dogfight meant almost certain death or capture. American pilots flying Mustangs with Packard Merlins developed aggressive habits. They pressed attacks knowing their engines would respond to throttle demands. They pursued enemies confident their power plants would bring them home. The production achievement represented by the Packard V-1650 program was as impressive as the technical accomplishment. At peak production in 1944, Packard's Detroit facility produced over 2,000 engines monthly. This required coordinating thousands of workers, managing supply chains for hundreds of components, and maintaining quality control standards that ensured every engine met specifications. The company employed over 30,000 workers at its Morse Avenue plant, operating 3 shifts around the clock, 7 days per week. The workforce included significant numbers of women who proved remarkably skilled at the precision work required for aircraft engine manufacturing. Rosie the Riveter became a cultural icon representing female war workers, but at Packard, women worked as machinists, inspectors, and assembly technicians on tasks requiring extraordinary precision and attention to detail. The quality control records show no statistical difference between engines assembled by male versus female workers. Skill and training mattered, gender did not. Quality control procedures at Packard set standards that influenced American manufacturing for decades afterward. Every component received multiple inspections during production. Critical parts like crankshafts and connecting rods were X-rayed to detect internal flaws invisible to surface inspection. Completed engines underwent dyno testing, running on test stands under load while technicians monitored performance and listened for any irregular sounds that might indicate problems. Only engines that passed all tests received approval for installation in aircraft. This obsessive attention to quality created engines that could be trusted absolutely. When a maintenance crew installed a freshly overhauled Packard V-1650 in a Mustang, they knew with confidence that the engine would perform exactly as specified. There were no surprises, no hidden defects, no manufacturing flaws waiting to cause failure at the worst possible moment. This confidence flowed from manufacturing floor to flight line to combat operations, creating an operational advantage that German industry, struggling under Allied bombing and resource constraints, could never match. The strategic implications extended beyond individual aircraft performance. The U.S. Army Air Forces could plan campaigns knowing that their fighters would be available in predictable numbers. When planners scheduled the massive bombing raids that devastated German industrial capacity in 1944 and 1945, they calculated fighter escort requirements based on reliable operational availability rates. Those calculations depended entirely on the Packard V-1650's demonstrated reliability. German military planners faced impossible calculations. How many fighters would be available for defense when engine failures were unpredictable? How could they concentrate forces when mechanical problems might reduce any unit's strength by half without warning? The Luftwaffe's defensive strategy against Allied bombing campaigns was compromised fundamentally by engine reliability problems that prevented them from maintaining the force levels required to contest Allied air superiority effectively. By mid-1944, the air war over Europe had been decided. The decision didn't come from a single dramatic battle, but from the cumulative effect of thousands of missions where American aircraft, powered by reliable engines, appeared over German targets day after day, while Luftwaffe interceptors, hampered by mechanical problems, couldn't sustain the sortie rates needed to defend German airspace effectively. The Packard V-1650 didn't win the air war alone, but it made Allied victory inevitable by ensuring that American fighters could maintain operational pressure that German forces couldn't match. The engineering achievement represented by the Packard Merlin influenced post-war aviation development profoundly. The emphasis on manufacturing precision, quality control, and reliability as fundamental design requirements became standard practice in American aerospace industry. The lessons learned producing 55,000 aircraft engines to exacting tolerances under wartime pressure informed how American companies approached jet engine development, missile production, and eventually spacecraft manufacturing. Hauptmann Werner Schroer, the German pilot who began our story, survived the war. In post-war interviews, he spoke with professional admiration about American aircraft and their power plants. He described the growing realization among German pilots that they were being defeated not by superior tactics or braver enemies, but by industrial capacity and engineering reliability they couldn't match. The Packard V-1650, he noted, represented American manufacturing philosophy at its finest: mass production without compromise in quality, consistency without sacrificing performance, reliability achieved through precision rather than artisanal craftsmanship. The last Packard V-1650 rolled off the production line in September 1945 after the war's end. Total production reached 55,239 engines, each one capable of running 100 hours between overhauls at full combat power. The Germans, who'd built sophisticated and powerful aircraft engines throughout the war, never imagined that American mass production could achieve reliability they couldn't match despite their reputation for engineering excellence. The irony was profound. German industry, celebrated for precision and quality, produced engines that required frequent overhaul and failed unpredictably. American industry, known for mass production and assembly lines, produced engines so reliable they redefined what was possible in aircraft powerplant performance. The Packard V-1650 proved that manufacturing philosophy mattered as much as engineering brilliance, that consistency trumped individual craftsmanship, and that reliability was itself a weapon as decisive as any gun or bomb. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.